Now I'm going to have to brutally context switch you all away from TLS to something completely different, as they say. This is, I'm presenting on behalf of my colleagues both at Yale University and EPFL who are involved in this. So what's the problem we're trying to solve? Well, the internet networking ecosystem depends on a lot of different types of authorities. And well, you know, hopefully they're always trustworthy, right? But, well, not quite, as most of you are all well aware. They get certificate authorities get hacked, randomness or lottery authorities get hacked, code signing keys get accidentally leaked or even just accidentally uploaded to the internet for everyone to sign their own malware with. Even really, you know, very basic functions like telling the time is surprisingly fragile, as we've been learning. And so in this talk, I want to talk about, you know, first about the trouble with trusting all of these authorities, and then kind of set out a grand challenge of figuring out how to decentralize the authorities, and then present a first baby step toward that, which is achieving transparency through what we call decentralized witness cosigning. And I'll present a particular scalable protocol to implement this, an evaluation, some comparison with prior transparency approaches, and conclude. So what is the issue with all these authorities that we're depending on? Well, the issue is any user like Alice, when her client or her device needs to do anything, like synchronize the clock, browse the web, send a text message, download a software update, she's got to know how, her device has to know how to securely connect to all these services. And that typically relies on deferral to some authority, right? So some authority has to say what Amazon's SSL public key is, or Bob's IM public key, or the latest version of this iOS or an application. And this typically happens by the authority signing some kind of statement saying, here's the time, the Bob's public key is X or whatever, right? The hash of the latest iOS is Z. Now, this leads to a number of problems. The most obvious one is, well, what happens if the authority is compromised in some way? Well, a compromised authority allows an attacker to create lots of fake, fake versions of these kinds of services and misdirect clients into doing really bad things and basically affecting a lot of clients at once. A second compounding problem is that client machines often depend on a lot of different authorities, and they kind of accept anything that a lot of, like, hundreds of CAs say as the truth, which means the attacker only needs to find the weakest link, the easiest to attack. And the attacker wins. So we kind of get weakest link security. Another slightly more subtle problem is because most of these statements that authorities made are cryptographically validated, secret keys are portable. If an attacker is not constrained to compromising an authority in place, they can kind of leave it there, the version in Freetopia that let it behave correctly, but steal the key and take it somewhere else in the world and create an evil twin, or as many evil twins as the attacker wants. And use it on the attacker's turf in a more controlled environment where the attacker can reduce the risk that the attack will be discovered, right? So this is, and we'll come back to this later. But then finally, the fourth problem is that just increasingly kind of everyone wants into this compromising authorities kind of pastime these days. Governments around the world, including governments fairly close to home that like to try to compromise software update type authorities, let's say. So what can we do about this? So I'm going to make a bold claim that, well, maybe not very bold, that we should just have to assume that no individual hardware, platform, software system administrator or authoritative organization can be expected to be completely invulnerable to compromise or coercion. And we need to do the very old, conceptually very old thing of splitting trust more widely. And we need to build systems that, that resist compromise by individual participants and build strong, move weakest link architectures to strongest link architecture. And I think a nice example of how this is kind of done is in the way that Tor handles its authority. Tor needs a somewhat centralized authority called the directory authority, but it's somewhat decentralized too by splitting it across 9 or 10 different nodes that have to kind of have a majority vote, have to kind of sign off in a majority on any view that the Tor clients will authorize. Now, so this is great. This is better than purely centralized, but we can ask the question, given the level of sophistication and motivation of a lot of attackers, is it unrealistic that some attacker somewhere might be powerful enough to either hack or coerce and steal the secret keys of, say, 5 critical directory authorities, and use those, be able to use those to create create fake versions of the Tor directory or any other directory for targeted clients. So this is where the kind of the second key point comes in, which is scale. So we need to raise the compromise threshold, not just from one, weakest link security of 1 to, a few devices needed to be compromised. But for really security critical things, I think we need to raise the compromise threshold and figure out how to build systems where it would hundreds or thousands of parties around the world would have to be compromised in order to break the system completely, right? And I'm not going to claim that there's a particular magic number in terms of the scaling that we need to get to, but I'm just going to say that we need to architect systems so that we can split trust so that incorporating all the diversity that makes sense is possible. So for example, could we envision decentralizing the TLS certificate process across all of the hundreds of certificate authorities? Could we decentralize DNS root zone signing across the thousands of global TLDs and so on, right? So that's that's a totally hand-wavy grand challenge. See my hands waving. This is not going to happen anytime soon. It's hard, but we can take baby steps, right? So what kind of baby steps we can take? So the baby step I want to focus on in this talk is just ensuring transparency. So we can't necessarily ensure that the authorities are going to be good or going to be not compromised, but can we make sure that whatever they do, they're exposed to public scrutiny? And in particular, we're going to try to ensure one particular very simple security property, namely that whatever the authority signs, good, bad, or indifferent, good, bad, or ugly, whatever you want to say, is going to, before any client is going to accept it, any signed statement has to have been exposed to public scrutiny, witnessed per se, and verified as having conformed to any checkable standards might exist. Now, the important thing about this transparency focus is it's actually, we don't have to completely redesign the authorities. It's practical to retrofit and add this to existing authorities without changing their logic too much. And so this is where decentralized witness cosigning comes in. So we assume we have an authority that does whatever it does already. We don't necessarily modify it much, but we now have a cloud of whatever size of witnesses that work with it to sign whatever statements the authorities make. And so now the authority is not just individually signing those statements, but the witnesses have to contribute to those as well. And every time a witness signs a statement, it logs it. It just makes sure that the statement exists in a public log so that security researchers or whoever can analyze it. And of course, clients need to verify that, that not only the authority signed the statement, but some adequate number of witnesses also did if they want some real protection from this. So that's the simple idea, right? Not too complicated. Now, you're going to ask, well, how do the witnesses know that these statements are good? Well, the answer is they don't. That's not the point here. Very likely, only the authority really is going to have the information knowing about who a particular public key belongs to or how a particular software image was created. But the important point is that even regardless of what they don't know, the witnesses can still ensure transparency. Namely, they can enforce the property that anything that was ever signed in a way that will be acceptable to clients has been exposed to public scrutiny. So if the authority is coerced or its keys stolen and used to do something bad, the attacker has to send the malicious statement through at least some number of the witnesses as well, thereby exposing the bad statement to public scrutiny. Of course, software images could still be backdoored, but that backdoor has to, in some sense, hide in plain sight. It can't be confined to some remote part of the world where nobody else is ever going to look, right? So how can we make this work in practice? And that's the focus on the next kind of more technical part of the talk, where we talk about making collective signing for this purpose scale. Now, we're using absolutely bog standard, very old crypto, well understood, just standard Schnorr signatures, but we're going to collect a group of standard, a list of public keys into a group representing a set of witnesses. And we make some assumptions, important assumptions that are detailed in the paper. But basically, we're using just standard Schnorr signatures, which is a commit challenge response protocol. Just to kind of refresh, the signer creates a secret, commits to it. A hash function produces a challenge, and the signer produces an appropriate response. The verifier uses those to reconstruct the commit and check it. So there's nothing new or important there. And it's also well known, already well established, that this can be extended into multi-signature protocols where multiple participants work to create one signature. Basically, the way it works is you combine the public key using the standard homomorphic properties of the crypto system. Each node creates its own commitment. We aggregate the commits, compute a collective challenge over the aggregate commit, and then each node has to produce its corresponding part of a response. And then the result is a single signature that's checkable in exactly the same way, but this time against the aggregate public key instead of an individual public key, right? So that's simple, that's old, we definitely didn't invent that. Our contribution is to try to make this practical, especially at scale. And so to do that, we brought in a bunch of other old techniques in networking, namely just things like aggregation trees. So what the CoSi collective signing protocol does is it organizes all the witnesses into a tree. And basically, for each signing round, we just have to do two round trips, 4 phases over that tree. Announcement, commitment, challenge, and response. Phases 1 and 3 are basically just broadcasts, tree multicasts. The only not completely trivial ones are commit, where all of the nodes produce their Schnorr commitments and then aggregate them gradually going up the tree. This limits each node to having to do basically a constant, small amount of work going up the tree. And then we produce the collective challenge based on the aggregate commit. That gets announced down the tree, and then in the response phase, we again go up and aggregate the corresponding pieces of the response, right? So pretty simple. An important caveat, what happens if one of these servers is missing, right? So, unfortunately this happens, and it's certain to happen if we have 100 or 1,000 witnesses, right? So we got to be able to deal with that. Fortunately, it's not too hard. There's various ways to do that that we explore in the paper, but the simplest way, just to summarize, otherwise is if one or more servers are down, we just proceed anyway. We create a collective signature that's not going to, based on a modified public key, that we just basically subtract out the public keys of the missing server and create a collective signature for the remaining ones that did participate. And then in the collective signature, we just include a bit mask that says which witnesses did and did not participate. The verifier can use that bit mask to recompute the appropriate collective public key for the set of servers that did participate, and therefore check it that way. This also preserves the transparency, ensures that the verifier knows exactly which witnesses did and did not participate, and allows the verifier to use non-trivial, maybe not just a simple threshold, but arbitrary criteria to decide whether the signature is acceptable or not. Okay? So there's a bunch of variations and details. I'll just refer to the paper. The next question, though, is how scalable and useful is this? So we experimented with this on DeterLab to see how far we could push it in terms of scalability. We managed to push it up to like 32,000 nodes. Server processes running across 64 physical machines. Of course, at those scales, these are heavily oversubscribed and running dog slow just because of their oversubscribed. So in a sense, these are conservative results, at least for the large scales. But we also imposed 200 millisecond round trip latencies to simulate really wide area latencies. Even at these fairly conservative configurations, basically the upshot is CoSi, with these techniques, CoSi scales really easily into the thousands of witnesses and even into the tens of the thousands, whereas kind of the standard approaches like Shamir secret sharing or just collecting a bunch of individual signatures runs out of steam a lot earlier. Similarly, with verification cost, if you can cache the right aggregate public key across verification rounds, the cost is basically flat, regardless of just the cost of a single conventional signature verification, regardless of the number of the size of the group. And finally, the actual signature size, since we're only storing a bitmap instead of a whole bunch of signatures, we get basically about a 500x size shrinkage with respect to just a bunch of ED25519 signatures. I'm running out of time, so just a quick comparison with prior. You might have heard of prior transparency approaches like certificate transparency and various ones in this domain. The important distinction is that prior transparency approaches require everybody to gossip. So you have these witnesses that watch the authority. If the authority goes bad, then all of the other stakeholders kind of has to compare notes and gossip in order to notice that something's wrong. Now that's going to work great if everybody lives in Freetopia and can communicate without restriction. But what if say Alice is in a different country called Tyrannia, where she's behind a great firewall run by the evil General Rex and can't actually get to most of these good servers and can only get to the bad compromised authorities and fake log servers, right? So the point is, if you're dependent on gossip for transparency, that can fail in any context where the attacker can prevent or control the gossip. In an extreme scenario, what if the attacker actually controls the target device and wants to, say, secretly coerce the device's vendor to sign a backdoored software image? Well, you might remember something like this kind of happened recently, although not all governments are always quite so forthcoming as the FBI was in this case about what it wanted to do. So the point is, a phone that's sitting in a sealed forensics lab can't gossip to report the backdoored software image that was signed by whatever, secretly signed. But if the device insists on seeing a signature that already encapsulates, binds in the certification that this thing was widely seen, there is hope of dealing with this kind of, at least ensuring that we know when something like this is happening. So in conclusion, it works, it's there. You can get the code in a binary and source form. We're trying to make it very easy to incorporate it in applications, other kinds of authorities. And it's, of course, still experimental, but there's a lot of ways to deploy it and experimentally, and we want to work with anybody who's interested. So finally, collective signing has other uses. If you're interested in blockchains, come to Usenix Security and see Lefteris, my student, talk about how to use them to improve blockchains. So in short, we need to decentralize the authorities, but as the first step, let's make them all transparent with decentralized witness cosigning. So thank you, and I guess there's not much time for questions, but that's up to you.
Okay, two quick questions.
Quick question. So, great, thanks. I really liked it. So, when you first showed the bit about, well, what happens if servers go away, first thing I thought is, well, you could do the Shamir secret sharing. And then you showed the Shamir secret sharing is really ridiculously more expensive, and that really surprised me. So how are you doing the Shamir secret sharing that made it so bad?
Well, so Shamir secret sharing is only that bad if you don't want a trusted dealer. If you don't want to trust a dealer, then everybody's got to share a big polynomial, and then everybody has to combine everybody else's polynomial, and you've got to do that every signing round, right?
Oh, every signing round.
Yeah, yeah, because of the commits. The commits have to, so now this is specific to Schnorr signatures. If you do this with BLS signatures, Dan Bonet actually very helpfully pointed this out, you can get around that potentially with BLS signatures, right. But with Schnorr signatures,
I think you actually can get around it with Schnorr signatures.
Maybe, yeah, that's quite possibly. Maybe we're doing something stupid there, but okay. Yeah. Mm-hmm.
Yeah, can you, John South, can you talk a little bit about how things work that change over time, like time, or maybe you get geolocated IP addresses or something, and you sort of, there's a natural inconsistency in those things?
Can you clarify what's changing over time?
So for example, the simplest one is time. Right? So you get something, it's 3 o'clock. No, it's 3:01.
Yes.
No, it's 3:02.
Yeah. So great question. So I didn't have time to go into so one of the things our prototype does is it provides a scalable timestamp authority with freshness proofs as well. And this can be incorporated with the rest of the thing. So all the witnesses, the initiator proposes a timestamp, says, I declare that it's this time, and then the witness servers can check that this is at least sane, within a plus or minus, I don't know, a minute, 10 minutes, whatever window you want to say, and they're not going to sign off unless that time is reasonable. And that can also sign atop of a Merkle tree full of challenges submitted by clients, and that way the clients can be sure that whatever timestamp record they got is not replayed. So that's kind of the very, very quick high-level summary, but we can talk about it more offline.